Hello. Okay. Um, I'll show that I can compile my code. Compiles without errors. Now I'll run my program, and I'll show that I can run programs in the background. So you see the job message being declared. Then I'll be able to list my running programs using the PS command. As you can see, these are the programs that I ran in the background, and I'm able to kill them as well by specifying the PAD. And as you can see, they print done messages when they are terminated. And when I call PS once more, it's an empty list because there are no programs running in the background. Now moving on to the code that handles the SIGINT. I have a handler in my mice file, which handles the SIGINT signal, and I set it up in the main file in mice. So specifically, when my program is expecting input from the user, I have a loop. I have a flag called SIGINT received, and it is declared over here. In a while loop in the get input function, which is called over here, I read from standard input. And if I get a signal interrupt signal, I return 0 from the get input function. If the return value of get input is 0, then I continue the loop, skipping the rest of the processing, and I return to the top. When the SIGINT handler senses that I got signal interrupt signal, it sets the SIGINT received flag to high. Since that flag is high, this new line message is displayed and the flag is reset. Then the prompt is displayed. As you can see, in the terminal, the SIGINT was received, but mice continued as normally. Then moving on to when a built-in is executing, I have another global variable, the foreground process ID, declared in my input output helpers file. In execute pipeline, I fork, and once the child is created, the child returns to the default signal handler for SIGINT. The same thing happens in my process line function. These are both functions where I execute commands and built-ins. As you can see over here, the signal handler is the default signal handler for the child. After the fork process, the parent puts the foreground process ID to the child's PID, and it waits until the child is finished. If you put a signal interrupt during the child's process, it will break out of the loop, and simultaneously, the signal handler for mice will receive that signal interrupt, and it'll kill the child process and set the signal received flag to high. Then, after you break out of the loop, this will reset that foreground process ID to -1, and it will return the function. After process line is returned, usually it'll be at the end of this loop, and the signal received flag will be high, so a new line will be displayed. And then it will print the prompt once more. An alternative approach that I could have chosen is I could have used the SA restart flag in my signal handler. This would have made system calls like read, which I used in my get input function, to automatically restart after a signal instead of returning -1 with the interrupt, like what I do. Then my input loop wouldn't rely on the failure of the read call to restart. I opted not to choose this option because the SA restart flag changes the behavior of other system calls as well, including write and wait. And it led to subtle bugs where some system calls didn't need to restart, but they did. And that was making it harder to pass the tests that were specified. Also, using SA restart would have reduced my portability to older Unix systems that might use my shell program. Whereas my approach gave me more fine-grained control when it came to expecting input from the standard input versus executing a built-in function. Moving on to code that handles receipt of messages. In my server, I have a background server helper function. And in this do while loop, I accept connections from clients and I go through a linked list of my client sockets. If I get a read from the client and I receive a message and they don't have a client ID, I will set their client ID. Then I will call the get message function that is defined in my socket file, and I will read their message. If the message is the connected flag, then I will show the client how many clients are currently connected and then free that message and continue. Otherwise, I write the client ID, the colon and space, the message, and I print that to the shell of the to the console of the shell that launched the server. When it comes to too long messages, there are two places where I detect this. One is in the client function over here, reading from standard input. So when the client sends in a message to standard input, it is put into an input buffer. And if that input buffer is longer than the max user message, then I will display an error and return. But if the message is not longer, but it expands into tokens that are longer, that is another situation. So I write a copy buffer. I copy the input string into a buffer and I tokenize that input and then expand the variables of those tokens. And I do a token by token check. Basically, I add a token to the constructed message and I calculate how much the token and a space would be. And if that is longer than the max user message, then I set a too long flag to high and I free the expanded token and break out of the loop. Then if that too long flag is set, it won't write the message to the socket and it will display an error and break and return. When it comes to sending messages using the send command, I do the same approach. I construct the message token by token, and I check if the size of the token incoming and a space would be longer than necessary. Then I display an error and return. Some pros and cons to my approach include my ability to check the message length before each token makes it so that I avoid constructing an invalid message and discarding it later. And I also never transmit a truncated message. I either send the whole message or none at all. However, some cons include, since I'm tokenizing input to estimate the length, I am tokenizing also again to see what the size would be after I expand the variables. And this wastes some CPU cycles and some memory. Also in my server loop, where I read from multiple client sockets, one by one in this loop. If a client sends a very long message, I may block on that socket, and that may delay other clients from receiving or sending messages to the um to the server.